Okay, dear friends, dear participants of our series of seminar. Today we happy again to see our colleagues Roman Nedela from Czech Republic, and he will talk us about the fundamental group of a graph and its properties. So Roman, you are very welcome, please.
Okay, hello everybody. So this is the second in the series of my talks. Last time I finished the definition of the fundamental group of the graph. The structure of the fundamental group of a graph with semi-edges is slightly different from the standard situation. If a graph has no semi-edges, then the group is free group of rank beta, where beta is the cycle rank. But if there are semi-edges, then each semi-edge contributes by factor Z2 in the free product. So we have as many Z2 factors as is the number of the semi-edges plus E minus V plus 1 Z factors. So I'm just repeating something from previous talk. There were some questions. For instance, how the connected graphs with trivial groups look like. Well, these are precisely the trees, because if the group is trivial, then the graph must be simply connected, but this, in this particular case, means that there are no cycles and no semi-edges, and such connected graphs are exactly trees. How about graphs with finite fundamental group or abelian fundamental group? Well, usually the group is not finite. So if it is finite, then either it is trivial and then the graph is tree, or it has exactly one semi-edge. So it is tree with one semi-edge attached. Whenever we have either a cycle or two semi-edges, the fundamental group becomes infinite. Almost the same story for abelian fundamental groups. It is equivalent to the question when a free product of Z's and Z2s is abelian. So this happens only if it is trivial, if it is just one semi-edge attached to a tree, because then the fundamental group is just Z2, or we have unicyclic graph, exactly one cycle. So it is a cycle with some trees attached, and then the group is isomorphic to the infinite cyclic group. Okay. Now something which is well known from the algebraic topology. The first lemma in the theory of graph covers is the unique walk lifting lemma, and it states that whenever you have a walk in the base graph, say based at the vertex u, and if you fix vertex u tilde in the fiber over u, then there is a unique walk w tilde based at the vertex u. Okay, so let me use advantage that I can write. So how the proof goes. So here is a graph, say y. Here is a graph x covering y. And here over a vertex u, we have some fiber. So here is u, and here is u tilde. Because we have a covering, so if the path or if the walk is just one dot x, and the covering is locally bijective, there is exactly one guy here. So for such a simple walk, it works. But then we can let's say there are more darts. Then we can extend this idea because over this vertex, again, the mapping is bijective. So there is exactly, if this is x1, and if here is x2, then there is exactly one guy how to continue, and so on and so on. So it is more or less easy statement, but it has several interesting consequences. And here there are some of them. For instance, we have a monodromy action. That means the fundamental group, elements of the fundamental group of a graph permutes elements of in the fiber. How this can be understood? Instead of general walk, we now consider closed walks in the base graph. And again, we have this situation. How this closed walk is lived? Due to unique walk liftinglemma, for each guy, there is exactly one lift, but it may no more be closed. So it can look like this. Here it can be closed. Here it can be like this. So what we are getting, okay, sorry, this is not, okay, it's okay, it's okay. So what we are getting here is because of unique bulk lifting, let's say we have x1, u1, u2, u up to un, we are getting a permutation. So a lift of any walk, any element. So we may imagine that it belongs to, if this is u, to the fundamental group PUX, it defines some permutation of the guys. And the permutation is defined, I associate to U1 that lift where this lift, this unique lift terminates. So it can be U3, for instance. So we are getting, for each element of the fundamental group, we are getting some over U. And this holds for any vertex. Actually, the fundament, if the graph is connected, the fundamental groups are conjugate. So there is no problem. So there is some action of the fundamental group on fibers, and this action is called monodromy action. Monodromic action is very important in study of coverings. For instance, it is natural to ask under what condition, if you have a covering, even and with Y connected, when X is connected, the cover. And the reply, the classic reply is, it is if and only if the monodromy action is transitive. No matter which fiber you take, the actions are equivalent in a sense. So this is one group related to the covering. With each covering, there is an associated a monodromy group of monodromies. I have to say that this action is usually not, it is not a permutation action because the core may be non-trivial, right? But if we factorize with the core intersection of all stabilizers, then we can get permutation action. So this is monodromy action. And we have a monodromy group, which is a subgroup of the symmetric group, group of all permutations acting on a fiber. But then there is another group associated with a covering, and this is the group which satisfies this condition. P is a covering, so it commutes. And again, so what it says is here we have a covering, and it says this. So there may be some automorphisms of the cover which satisfies these commuting diagrams. In other words, lifts of identity, right? And these coverings, these automorphisms obviously form a group, and this group is known as the group of covering transformations. Sometimes it is denoted by CTP. So it is a subgroup of the automorphism group of the cover. In some cases may be trivial, in some cases may be transitive. And there is a nice consequence of the unique-Vogue lifting, namely that the action of this group of covering transformations is always semi-regular on the dots. There is a group theoretical point of view to this statement. Namely that if we have this is a general statement from permutation group theory. Suppose the monodrome action is transitive. Then if you look the definition of the group of covering transformations, then this is nothing but the centralizer of the transitive action. And there is a general statement that centralizer of the transitive action is always semi-regular. That means stabilizers are trivial. It follows that the size of the monodrome group is the size of the group of covering transformation is always less or equal than the size of fibre over a vertex, which is defined like this. So this group of covering transformations cannot be too big. Another consequence of the unique Vogue lifting is that we can talk about foldness of a covering. Because if we have a covering between finite graphs, then there exists n such that any two fibers have the same size. How it follows from the unique Vogue lifting? Well, so what I'm saying is that every vertex and actually every dot has the same number of pre-images. So take a fiber. We assume that the guy is connected. So there is some edge to, there is some neighboring vertex. And take this fiber. But because of unique Vogue lifting, this edge is mapped to a matching between the two fibers. So the size of this guy is the same as the size of this guy. And using connectivity of Y, we can extend this observation to the whole graph. Of course, sometimes it is useful to consider also infinitely folded coverings. So then it just says that if one fiber is infinite, then all the fibers are infinite. The other consequence is, what is the, I already mentioned a bit about this. What is the connection or what is the relation between the two groups associated with a covering? The first one is the covering transformation group, the other one is the monodrome group. So if n is the foldness, then because of semi-regularity, we know that the size of this guy is always less or equal. And because of transitivity of the action, and transitivity is equivalent to the connectedness of the graph X, and this is our usual requirement, this group is at least as large as n. Interesting case happens when here is equality. Actually, one equality implies the other. So it cannot be that on one side you have equality and on the other side not. And this is one of the equivalent definitions of the regular coverings. So the covering is regular if the CTP acts regularly on each fiber, or and even only if the monodrome group acts regularly on the fiber. Okay, so this is very important that this each covering is n-folded for some n. And now even more interesting statement. This is sort of, I mean, today I'm presenting a classical approach to graph coverings, because this is, all these ideas and concepts are well known in algebraic topology. So there is a correspondence between the subgroups of the fundamental group of the base graphs and coverings over Y. And here is the correspondence theorem. Whenever we have a covering from X to Y, then the covering P induces an embedding, that means a monomorphism of the fundamental group of the upper graph into a fundamental group of the base graph. And it holds also in the reverse direction. If one fixes a subgroup H of finite index n in the fundamental group of the base graph, then one can construct a covering with X connected such that the fundamental group of the upper graph is isomorphic to the prescribed group H. So it works both ways. This is quite important statement with many consequences. So let me prove statement A. What are the elements of the fundamental group of a graph? These are closed walks based at X, based at W, and based at V, and this means just relation of contractibility. But in graphs, the only way how to make an elementary contraction is to go one way and return. So you have something like this. And if you don't have something like this, then then the walk is called irreducible. So instead of these brackets, I can choose irreducible walk, which is uniquely determined for each class. And naturally, we set P star of the class to be class of PW. And here is the argument, because such a elementary contractible walk is projected onto elementary contractible walk, then equivalent walks are mapped onto equivalent walks. Therefore, P star is well defined. All the other things just one gets immediately. So once this is good, well defined, it is a homomorphism, and vice versa, because you can read this from the reverse, from the right to left. Since lift of a contractible walk is again contractible, the kernel of this mapping of this homomorphism is trivial, and therefore it is an embedding. So this way is easy. For the other way, we have to construct the covering. I will come to this later. But let me discuss something. every group contains a trivial element as well the fundamental group of a graph. So there must be an associated covering if the correspondence theorem holds. So to the subgroup, to the trivial subgroup, there must be some associated covering. And this guy, which corresponds to the trivial subgroup of the fundamental group of X, this cover is called universal cover. And by the correspondence theorem, so this is the reason why it is called universal cover. If something covers X, then it is covered by X tilde. So we have this, here is X, here is this universal guy that corresponds to trivial group. And here is some covering. But because of correspondence theorem, the fundamental group of this guy embeds here, and of course it contains one, so it must exist also this guy. So it is universal. This is the universality actually, that for any covering P, this universal cover covers any cover of X. There is a nice observation. Suppose we want to count all the n-folded, let us fix n. Suppose we want to enumerate all the n-folded coverings over a finite connected graph Y. Well, then, because of this correspondence theorem, this depends only on the cycle rank and on the number of semi-edges, because there is a correspondence between subgroups and coverings. So what does it mean? That it means that the number of coverings is the same as the number of subgroups in the fundamental group of the base graph. So here we are assuming X, Y, X covers Y of index n. So if we are able to count the number of subgroups of index n, this is the same as to count the number of all covers over Y. But the group, the fundamental group, suppose there are no semi-edges. The fundamental group is just free group of rank beta. So the question about enumeration of coverings converts to the question of enumeration of subgroups of a free group of rank beta of index n. And sometimes we are in a situation that we want to count covering or covers over a graph with semi-edges, but we don't want semi-edges. So we are in this situation. This may contain some semi-edges, some singular guys, but this here we don't wish them. How to understand this in the language of subgroups of the fundamental groups? This means we are interested into torsion-free subgroups of index n. So no elements of finite order. So this is also somewhat standard situation. So if you know algebraic topology or theory of Riemann surfaces, it recalls you something. Subgroups of a free group. Using these ideas, the correspondence theorem and so on, we can prove the theorem by Grushko. What says Grushko theorem about subgroups of free group of rank beta? It says the following, that if we fix the index, then there are, first of all the subgroups of index n are free groups, and secondly, we know the rank. So it is a simple function, linear function of n and beta. How to prove it? Well, we can take Y to be a bouquet of beta cycle. So what it is, if beta is 3, so we take, so this is V3, right? Take a subgroup of index n in the fundamental group, which we already know that it is a free group of rank beta. By the correspondence theorem, there exists a cover with where H is isomorphic to the fundamental group. Better to write here. Okay, some cover X, Px tilde V. And then we just count the Betty number of the cover. So what is the Betty number of the cover? Of course, what is beta? Beta is E minus V plus 1. And in the cover, this number is n times E, this number is n times V. So from this, we get the result. So it's almost easy. So as a consequence of the correspondence theorem, we are getting the Gruszko theorem. There are several problems and exercises which I'm not going to solve. I can maybe give some hints. So there is a problem 2.1. Suppose we have a 2 covers over X. Is it visible? Yes. So we have this situation. Y and Z. So the question is, and suppose all these guys are finite. The question is, can we construct some common cover X tilde covering both guys, and moreover we want to have it finite. Well, how to approach such a problem? Think about correspondence theorem. What does it mean in terms of subgroups? Similar dual question. Suppose a graph covers Y and Z. Then we ask whether there exists a joint quotient X bar, which is covered by these two, and we are interested in the largest such quotient, where largest means that there is no, well, it is self-defining. There is no common cover covering this guy. Again, if you want to, good approach is to think about the correspondence theorem and to translate the problem to problem about subgroups of the fundamental group. There is another problem. Try to formulate and prove an extension of the above result employing graphs with semi-edges. By the above result, I mean, I was restricted to graphs without semi-edges. So what it says about this, I mean, Gruszko theorem for products, free products of certain number of Z2s and certain number of Z's. And the last problem, describe the structure of the unit. This is also nice. I mean, it's good to understand, and here it is possible. For general spaces, it is a very difficult problem, but here it is possible to understand how the universal covers look like over a finite connected graph. And in particular, one can ask the following question: when this is finite, infinite, and what it is if X is a K-valent graph. K-valent means every vertex has degree K. Okay. between all coverings, regular coverings are of special importance. I already presented some definitions. So here there are several equivalent conditions. The first one says that the monodrome action is regular. The second one says that the covering transformation group is regular on a fiber. Then the third equivalent question is that the monodrome action and the covering transformation group of covering transformations are isomorphic. Also, it can be translated like this, that Y we viewed as a quotient of some subgroup which acts fixed point freely on vertices and darts. Actually, if you relax this condition, then you are getting an idea about branched regular covering, right? So if you relax the requirement to be free on vertices, then this is the way how to define regular branched coverings between graphs. Okay, for combinatorialist, the next equivalent definition is fine because it allows to construct a big guy from a small base graph. It says that there exists a Cayley voltage assignment, that means some mapping from the set of darts of the base graph into a group G, such that we can form a derived graph using this voltage assignment, and this derived graph covers Y. If you look Gross and Tucker book, then these guys are called ordinary voltage assignments. And the last is very classic. We have this induced embedding, and if this induced embedding gives, in general, we have a subgroup. If it gives a normal subgroup, then the covering is regular, and vice versa. If it is regular, then the embedding of the fundamental group of graph X is into the fundamental group of the base graph gives a normal subgroup. So there are many characterizations, and some of them are useful. If you start to think about this from the point of view that regular coverings are nothing but the natural generalizations of Cayley graphs, then you can recognize what is what. For instance, the monodrome group in Cayley graphs, this is this connection group from which it is created. And it is, if it may be given by right multiplication. What is CTP? For Cayley graph, it is a multiplication from left. And we know that left, in case of Cayley graph of regular action, the left and right multiplication groups are isomorphic, of course. So in other words, the regular subgroup is from the point of view of group theory the same as the Cayley group. And so on and so on. That's why we use the term Cayley voltage assignment. There is a difference between Gross and Tucker and our approach that we also consider semi-edges, but otherwise the definitions coincide. Switched. Few words about irregular covers, because these are also important in some considerations. Again, there are many equivalent conditions, but for instance, if the covering is irregular, the mono, and if it is connected, if X is connected and Y is connected, then the monodromy group is usually much larger than the Foldness, and the group of covering transformation is no more as regular action. It can be even trivial, right? And it is often trivial. If we are talking about combinatorial approach, instead of ordinary voltages, we use permutation voltages. What does it mean? What does it mean? Some simple example. For instance, take something like this. And talking about voltages, it is good to have some preferred orientation of edges. It is not important which one you take, but this is just because we know this, that Cx inverse is Cx inverse. It is enough to define voltage assignment from one direction, and for the other it must be inverse. And suppose we choose n equal to 3, so we want some three-folded cover. So what we do is I can take S3 symmetric group acting on 3 elements, and I randomly choose, for instance, here 1, 2, 3 permutations. 1, 2. Here it can be identity. Here as well identity, and here as well identity. And you may think how the covering look like. For instance, okay, so because n is 3, over each vertex we have 3 vertices. Because this is a spanning tree. So here there are ones. So if this is level 1, 2, 3, at each level, here is also 1, here is also 1, and here will be 1. At each level, we have just copy of this spanning tree. So we have something like this. And for 2 as well, and for 3, something is missing as well. So these guys were, I took so-called T-reduced voltage assignment. This means that I choose a spanning tree T, and I have chosen identity voltages there. Actually, we don't lose anything because every covering is in a sense equivalent to a covering which arises from T-reduced equivalent. And now, okay, so this it will be too much, so I will just take the two guys, the two orbits over these two vertices. So what does it mean that you have? So here we have 1, 2, 3. Here we have 1, 2, 3. How this edge is lifted? Because we have 1, 2, 3 here, it lifts in this way. And over each edge we mimic the permutation by perfect matching, and in this way a covering is constructed. And every covering, irregular or regular, can be obtained by the permutation voltage assignments. Okay.
Roman, some small question, please.
Yes.
Could you describe us what is core of monodromy group? Core of?
The core of monodromy action is actually the fundamental group of the X.
Yes, but in terms of monodromy group, this is stabilizer of a point or what?
Yeah, it is the stabilizer of the point, and all the stabilizers are conjugate, but if we are working with you mean in terms of voltages or permutation voltages?
No, monodromy is just permutation group, yeah, if I understand. Monodromy.
Yeah, it depends. So we can talk about monodromy action and monodromy as a monodromy group as a permutation group where we factorize by the core. The core in general is intersection of the stabilizers, and the stabilizer, each stabilizer is a fundamental group of the upper graph.
So there are no canonical choice of this code. This depends from this point, but all of them are isomorphic.
All of them are isomorphic, and no, I'm not sure whether they are the same or not. They may not be the same.
No, it's connected. Okay, so
yeah, they are conjugated, that's clear. But the intersection, this intersection of conjugated subgroups, this is what I can say.
No, you're talking about connected graphs.
Yes. Yes.
Okay,
yes.
thank you.
In the regular case, I know that all the guys are identical.
Yeah,
so
this core is identity. Yes,
the core is the fundamental group, actually.
Okay.
The core is trivial, yes, because in that case the action is regular, yes. And okay. You can just say the definition of the core.
Okay, thank you very much.
Okay. Well, sometimes it is easy to recognize that the covering is irregular. For instance, suppose we have a graph and we find a triangle here. And suppose over a triangle, there is a triangle and there is a hexagon. So if you have such a situation that a lift over such a walk, the lift of a cycle is always a union of cycles. And if the sizes of the cycles are different, then this is typical for irregular. So in regular covering, a cycle of length, okay, in general, Cn is covered by some union of Ci's, where I is a multiple. Each I is a multiple of n. And if you have different multiples, then this immediately means that the covering is not regular. But if they are the same, like you can get over a triangle union of 6 cycles, for instance, then you can, and if this happens for every cycle, you can deduce this is not enough for regularity. This is not enough, simply. So it is just one-way implication. If you have cycles of different size over a given cycle, then you know that it is irregular. But if you cannot find such an argument, then you cannot claim that the covering is regular. Also very important, from theory of groups, permutation groups, we know that every transitive group action can be modeled by action on cosets, by right multiplication on right coset or left multiplication by left cosets. So this happens also here. We can model the monodrome action by Schreier action, and this gives rise to the idea of Schreier voltage assignments. And because there were too many voltage assignments, some decades, 2 decades ago, with Sandy Malnich and Martin Škoviera, we were thinking about some unified theory of voltage assignments, and we found it. So just a little bit theory of actions. So what is an action? Action can be understood in this way. Take a homomorphism from a group into a symmetric group acting on some set omega. Then we can define action of a group G on omega as X alpha G, right? Where this is the natural right action by permutations. And actually, every action can be understood, every Corfi action, better to say, can be understood in this way. Okay. So what is a voltage assignment in general? In general, we can define it as a triple, where F is an abstract fiber, G is a group, and alpha is a homomorphism from the fundamental groupoid to an action of G on an abstract fiber. There are 3 popular voltage assignment where F and G, so this is a action. What is an action? You have a set, so this is this abstract fiber, and a group acting on a set. So if we consider Cayley voltage assignments, then we identify F with the group G and Gx by multiplication. If we have permutation voltage assignment, then the abstract fiber is just a set 1, 2, up to n, and G is the symmetric group on n. And if we consider Schreier voltage assignment, then the abstract fiber is formed by cosets defined by some subgroup of G, and again the action is by right multiplication. So these are the 3 most popular, but in principle you can take any this couple. So any abstract fiber and any action of G on F. And what is important is that we can define always a derived graph. But before, I want to mention 2 exercises. So the question is whether there are 2-folded irregular coverings, and in general, what is the least integer such that there exists an irregular and folded cover. The other question is find example of an irregular covering over a 1 latex graph with 1 loop and 1 semi-edge, where the loop lifts onto a homogeneous 2-factor. Homogeneous means that each connected component is a cycle of the same size. Okay, so now we can define in a uniform way the derived graph. So this is very combinatorial approach. We have a small graph and we want to define a large graph covering the small graph. Why this? Because coverings of graphs are perfect to check, to control local properties of graphs. I will next talk, I will come with some nice applications. But first we need to build a theory. So this is a generalization unifying all the possible derived graphs for all the possible voltage assignment. So suppose we have a graph. Let me recall that this is the set of darts. This is the set of vertices. This is the incidence function associating a dart. Here we have a dart, and it associates a vertex to a dart, right? So this is EX. Of course, we assume that these sets have empty intersection, and L is the dart reversing involution. So our idea about graphs is that we have a universe of darts completely free, and then incidence function makes stars, says which guys have the same origin, and the dart reversing involution creates edges. So this is a standard, but it may create also a loop, or some dart may be associated with the same dart, and then we create a semi-edge. Okay, and how a derived graph is, suppose we have a voltage, whatever it is. I mean, so we associate elements of a group, and this group acts on some abstract fiber. So what we do? We take the Cartesian product, D times the abstract fiber, the same for vertices, and we define the incidence function in a natural way. So what it is, X, and this can be viewed as a coordinate. X with coordinate F belongs to F, of course, goes to IX. So we mimic what happens in the base graph, F times action CX. Similar way, the dart reversing involution. So we inverse the base guy, and we let the voltage act on F. And the only required condition on C is this one. The inverse guys get inverse voltages. Why so? This is because we want to extend the guy to the fundamental groupoid and fundamental group. So we always can extend C to walks, from darts to walks, in a natural way. And this is a condition which guarantees that everything is fine. And in the end, we are getting a homomorphism or better epimorphism from the fundamental group to G. This condition, that what is this guy, GV? So as I said, we extend in a natural way voltage assignment to walk. We just multiply, we just read how the darts appear on the walk, and we take a product. And if we fix V, we can consider voltages of all closed walks. They generate a subgroup in general of G. And this here is equality. This is another condition guaranteeing connectivity. So this is equivalent to the fact that the derived graph is connected. Right? So it is natural to assume that the local group is always equal to G, but sometimes it is advantage to have possibility to relax this. And there is a standard lemma. The projection erasing the second coordinate is always a covering. So this is generalization of all the derived graphs used in literature. And if you are interested, you can find more information in our paper by Malnic, Koviera, and myself. 2000, I'm not sure, maybe 2000 or 2001, I'm not sure. European Journal of Combinatorics. Yeah, subgroups of the fundamental groups correspond to coverings, but somehow we have a feeling, even to prove the reverse statement. Okay, so what we have is a construction of the derived graph from a voltage assignment, and we want to prove that in a sense every covering can be expressed in this. Even to formulate this statement precisely, we need to have an idea of isomorphic and equivalent coverings. And this is also very important if we want to, so some of the coverings can be identified, some of the coverings are totally different. And this idea of equivalence between coverings is quite general. It's related with enumeration. So there are many mistakes in literature enumerating certain structures, which comes from the fact that it is not clear under which equivalence the objects are enumerated. So let me make it more precise. Okay. So as I said, the voltage assignment can be applied to elements of the fundamental group. Sorry. Can I continue?
No reply.
Okay.
No,
So as I said, the voltages on a connected graph can be applied to elements of the fundamental group. And if the local group is the same as the general group, then this mapping is a group epimorphism. And this is very natural condition, because this means that x to c is connected. So how about equivalence? Two coverings of, so we want to say under what condition two coverings are equivalent, and this means that there are two isomorphisms, phi between x1 to x2 and phi tilde between the covers, such that these guys commute. And there is some stronger relations which say that two coverings over the same graph, for instance, are isomorphic if there exists a graph isomorphism such that this is true. Maybe better to understand it on diagrams, on the correspondence diagrams. So what we do have, we have one covering which is called P1. We have another one which is called P2. And we want isomorphism here and isomorphism here. If we can find such guys, then the coverings are equivalent. What is the difference for isomorphic guys? If we are talking about isomorphic guys, here we have just identity, and here we are looking, so we have two covers over the same graph, and here we are looking only for some guy here. So this is equivalent. Equivalent, this means isomorphic. So the reverse statement to the construction of derived graph is that whenever we have a covering over X, there exists a voltage assignment permutation. Okay, if we are interested only in regular covers, then we want ordinary or Cayley voltage. If we are talking about general, we are talking about permutation voltage assignment, for instance, such that if we construct the derived guy, then here is isomorphism, and the whole diagram commutes, where this P2 is the natural projection arising the second coordinate. So this statement says that construction of the derived graph is universal, that you can model every covering using it. Short note about this scheme. So we have two coverings and two related isomorphisms. If here x1 is equal to x2, then we are talking about automorphisms. And this scheme is often used in this way, that choose an automorphism. And the question is there, so here we have also the same guy, is there an automorphism such that this diagram commutes? And then this is called lifting automorphism problem. This is especially useful in applications when you have as a base graph highly symmetrical graph and you want to extend the construction. So we want to construct infinitely many, for instance, guy. So this is a scheme. So you try to find, for instance, voltage assignment such that the whole automorphism group will lift. And if it is regular, then you are getting something very symmetrical. Yeah. Equivalence of coverings in terms of voltages. I have a good friend, Martin Škovera, and his first paper published in 1987 deals exactly with the problem of equivalence. In the paper, he derived an algorithm to compare two coverings defined by voltage assignments. So, the input are two graphs, actually one graph with two voltage assignments. And the question is, when the derived graphs are equivalent. So when the coverings defined by the voltages give the same covering, and here is the algorithm. First of all, to compare the voltage assignment, it is good to, there is a procedure how to reduce the coverings, how to reduce the voltage assignment onto T-reduced voltage assignment. So what is going on? Just simple example. So let the graph is K4. Let me consider, I don't know, Z5, for instance, Z5 plus. Let me put randomly the numbers here, 0, 1, 3, and here, for instance, 4, 1, 0, 2, 1, 1. So we have two voltage assignments in the cyclic group Z5, and we want to understand whether they define equivalent or non-equivalent covering. So what we do, following Covera's algorithm, we have to choose some spanning tree. So we choose the same spanning tree here and here. And it's good to direct the quadri edges. Again, not important, but it is technically fine. And now what we have to do is to transform both voltage assignments in the way that on the tree we are getting zeros. So let me do it here. So here we prescribe zeros, but on cycles, the voltage on each cycle is not changed. So, and it is enough to check fundamental cycles, of course. So what is the voltage on this triangle? So it is 1, but, where was the, so we need to choose arrows also here. Because it's not defined. By choosing arrow, I'm saying whether on this direction the largest voltage do or the opposite. Okay, so now it is completely defined. So what is the voltage on this cycle? It is 1, and because I'm running opposite direction, I have to do -1. So what I have counted is that on this quadri dart, in order not to change the voltage on cycles, I have to put -1, which is 4 in my group. How about this cycle? 1 minus 1 is 0 plus 2. So this is 2. So I have to put 2 here. And how about here? 3 plus 1 is 4. So I put 4 here. I do the same transformation in here. So here I put zeros. I have to add the arrows. And again, so I count 4 minus 1 is 3 here. 2 minus 1 is 1 here. And how about here? 1 plus 1 is 2. So it should be 2. So it is good to view these transformations like that. I have chosen the same coordinate system. So now I have the voltage assignment reduced with respect to the same spanning tree. Now, are they the same? Well, they don't look to be the same, but sometimes it cannot be seen from the beginning because also the group may have some automorphisms. So what I have to now is to use action of the automorphism of group of G on the voltages. And for instance, on this dart, I have 2, so I have to multiply this by 2. Multiplication by 2 is, of course, an automorphism of Z5. So if I multiply by 2, I'm getting here 2. 2 by 2 is 4. And here, 2 times 3 is 1. And now I have to compare. And now I see that here it is different. So the voltages are non-equivalent. So this is the answer. If I got 4 here, then they will be equivalent. Okay, so let's come back. So this was how to apply. So this is the first step. We reduce the voltage group to the local groups. And for the first step, this reduction is done no matter what is the voltage assignment, whether it is voltage, ordinary Schreier, or permutation voltage assignment. And so if it is in permutation voltages, I'm looking for a permutation sigma such that C2, here I understand this as a vector, right? Where it is enough to look the voltages on the Cottry dots. This is conjugation, but what is conjugation? Everybody knows that in the symmetric group, the group of inner automorphism, except S6, is the same as the group of all automorphisms. And here is the statement we have used because we were working with Cayley voltage assignments in the example. So the two T-reduced voltage regular coverings, the two T-reduced, it's something wrong here. Two T-reduced voltage assignments, ordinary voltage assignment, define regular covering are equivalent if there is a group automorphism. So we have to use in the end a group automorphism, and this is what we did. So we tried to compare the guys by the voltage assignments. There's a note for those who like Riemann surfaces. Voltage assignment can be viewed as a voltage assignment can be viewed as an epimorphism from Px U onto G. And two guys are equivalent what is the algebraic criterion if and only if C2 there is a okay, I may think that this is reduced to T1 and this is reduced to T2. The guys may not be the same. If there exists, so what says Coviera? If there exists A belonging to out G such that A C1 alpha, this is true. What is the alpha? This is the transformation of T2 reduced to T1 reduced. So I want to unify the three. Well, how about Riemann surfaces? In Riemann surfaces, we may have action of a group G which can be viewed as an embedding. Okay, we can think just on the case where on the orientable case, and this is the set of homeomorphisms preserving orientation. And there is an algebraic criterion derived by Riemann. There is an associated Fuchsian group gamma, and the action of G with that signature defining gamma exists even only if there exists a group epimorphism. So this group epimorphism is an analog of the voltage assignment, because voltage assignment is also some group epimorphism from the fundamental group. Here it is from the Okay, so if we have an action, we can form a quotient guy, and this is an orbifold. And this gamma is a fundamental group of O. So it is perfect analogy. And there is a criterion by Lloyd saying when the two guys are equivalent, and if you have two such epimorphisms, if and only if, so there is an algebraic criterion. If there exists A belonging to out G, perfect analogy with Scoviera, and alpha belonging to out gamma. But what is the Scoviera's transformation when we reduce with respect to T? Nothing but change of base. Change of base of the generating set of the fundamental group. Because choosing a tree, I'm choosing a generating set. So everything fits. Perfect analogy. With Sasha Mednik, we have a long-term project where we want to study such similarities between theory of Riemann surfaces and graph theory. So here is one example. Yeah, I didn't prove actually the part B of the correspondence theorem. So maybe now it's, I have 9 minutes, a good time to do it. So if you remember, so what says the correspondence theorem? If we have a covering, then the group of the upper graph, fundamental group, embeds into the fundamental group of the base graph. Vice versa, if we have a subgroup of the fundamental group of the base graph, we have to construct the covering. Now I'm ready to do it using Schreier voltage assignments. Okay, so take a subgroup of the free group of rank beta. Let the group is generated by beta generators x1 to x beta. And we can, with this free group, we can associate the base graph. The least possibility is to take the bouquet. But we can take any other graph with cycle rank, connected with cycle rank beta. And we can define a T-reduced Schreier voltage assignment by taking the group to be the fundamental group. F is the set of cosets, and we identify, okay, we take some spanning tree, there we put identity, and for cotridarts, we find bijection between, it doesn't matter which one, every cotridart will correspond to one generator. And by what we have done, there exists a covering, and F beta has monodromy action on the unique fiber over a vertex with the stabilizer H, but H is the fundamental group of the covering graph. In particular, H is free, so this is the other direction. So what I said is that using Schreier voltage assignments, one can prove the constructive part. Okay, so once we identified okay, so we understand that enumeration of coverings and enumeration of subgroups of prescribed index is the same, and actually this is related to so-called Hall's theorem, but I think my time is almost over, so I will stop here.
Okay, thank you very much, Roman, for very of these classical results about graph coverings. So some questions, please. Some remarks, some suggestions. I have a question. Could you say a few words about branch coverings? What is advanced? What is the perspective of development of the theory? That maybe very few words about.
Yeah. Yes. What we did for branch coverings is that part. What we did with you is finished almost finished. There is this Riemann-Hurwitz equation. So we found some, because if the covering is smooth, then there is a simple relation. If there are branch points and vertices, then the relation is more complicated. So there is a version of Riemann-Hurwitz equation.
So this is the first stage.
This is one of the steps. Which is done. Then there are some other steps which are done. For instance, a lot of can be done if we consider embedded graphs, because there the situation is more easier. If we are talking about, for instance, regular coverings, then we know that the stabilizers are cyclic. So it can be described by one number. If we are talking about general graphs and regular branched coverings, then in principle, any finite group can be a stabilizer. So it becomes more complicated. Then there are some analogies already discovered by some other guys. So there is a way, but except, okay, I see. Maybe what is more important is we can develop this theory, but important is to find non-trivial applications. So I see nice applications in study of maps and branched coverings between maps. This is here there is a field for finding some interesting applications. In general, okay, what is also, it is good idea to consider branched coverings over one vertex graph. For instance, if we consider regular branch covering over a graph, then instead of Cayley graphs, we are getting vertex transitive graphs. So this is of interest, people doing highly symmetrical graphs. So here we can find some applications. But I cannot say that I see the full picture.
Okay, thank you very much. Some more questions, please. Some remarks.
Yeah, I discovered this, what I have shown you about the equivalence and the correspondence between the Deutsch algebraic criterion for equivalence of actions of groups on Riemann surfaces and graphs. I knew both for some time, actually for a long time, but only recently I have discovered that these criteria are basically the same. They say the same. I mean, that's
very good observation. Yes, you're right.
So there are many nice observations, but so we can do, okay, what I can say is something general. One can proceed in two ways. Try to simplify proofs from the theory of Riemann surfaces using just graphs. So this is one way. So take some classical theorem and discover a new approach, how to prove it, or new ingredients. The other way around is take some interesting statements about the Riemann surfaces and try to deduce what does it mean for graphs. So this is basically the strategy.
What about Beck? You know a lot about graphs. Maybe you can try to find the similar questions. or even
For instance, I forgot to say that we have several good results about Jacobians, right? This is another big topic. So Sasha is an expert for this. So here there is a room for research. I don't know for about this is. Yeah, this stuff still I don't understand. For instance, what is the connection between the combinatorial properties of graphs and structure of Jacobian? I don't understand this. It's a very good question.
Well, this is more or less understandable because this is how to say. This does not depend from the spectrum of graph, not spectral properties, more delicate things. Yeah.
Yes, but
outside of our intuition, honestly.
Yeah, we have some implications, but we don't see the whole picture.
No, one application we discussed before your lecture with Sergei Orlov. This is just solving equation, classical equation. Delta Laplace operator of U is equal to F. So this is standard problem for Laplace operator, which is well known in classical analysis. How to solve this equation? For example, when the boundary values of this function are fixed. So this is Dirichlet problem, standard Dirichlet problem.
Yeah.
And the classical situation told us, if we have a just harmonic equation, for example, delta U is equal to 0, and suppose that boundary values are equal to 0, then function for sure is also identically 0. This because of maximum principle of harmonic functions. But in our situation, if you are talking about graphs and their application, the values of such a functions usually are inside of some finite group, inside of some finite ring. In this case, there are no maximum principle for harmonics. You can create a harmonic function whose boundary values is identically 0, but the function itself is not identically 0. And this exactly can be used, this Jacobian theory. Part of Jacobians are exactly responsible for such exotical solutions for harmonic equations. So Jacobians, kernel of Jacobians help us to find a non-trivial solution of classical equation delta U is equal to 0. In standard situations, this is 0 or maybe just constant. In case of graphs, there are many non-trivial solutions. And Jacobian exactly are responsible for description of such solution in very clever way. Of course, now just very few steps are done in this direction, but I think the future is very interesting. Okay.
Yeah. Many interesting problems. It would be nice to find some applications of this theory in other branches of mathematics.
Yeah, sure. Okay, some more questions? Sergey, maybe you want to ask something, you may ask in Russian. No.
I just want to tell students that if you have some problems, just write me a mail and we can have separate communications.
Okay. Well, if there are no more questions, let us thank Roman Nedela again, and we are waiting for his next lecture, which will be 2 weeks later, I think. Okay, thank you very much, Roman.
Bye, bye, bye.
Bye, bye.
Thank you, Roman. Thank you. Bye, bye.